Hi guys. So I'm here with my colleague Hari, who's also here on the call. So we're working together with an NGO called Dakshin Foundation to work on green turtles in the Lakshadweep archipelago. To so just to give a quick background, in the mid 2000s we had sorry, one second. Yeah. In the mid 2000s, we found a very big increase in green turtle abundance across the archipelagos, and that was something very interesting. And we wanted to study why there is such a big increase, and also what it means with respect to the resident seagrass population. Since the green turtles are major foragers, we wanted to know how their foraging strategies differ between places and how they're establishing new foraging sites and moving between islands. So as you can see here, the island, it's a very small island group. You can barely see the islands at all in the first place. But the turtles do move a couple of 100 kilometers between the islands to find patches of green grass. So we wanted to find out what's happening. So instead of buying commercially available tags, we wanted to develop our own GPS tags for the sea turtles. One of the main reasons being that we wanted to deploy them in larger numbers. So we wanted to develop something that's very, very low cost. So we started developing our own tags. So here's the tech part of it, so which is the development of the tags, which you're going to like very quickly jump into. First thing was the hardware design. When we started developing the tags, we went with the classic route. We took an AVR MCU, which is like an upgraded Arduino, and we slapped on a GPS unit and a flash to record all the data points. We took some peripherals, an accelerometer, temperature sensor, and a submersion sensor, and we added all of them and interfaced them with the microcontroller as well. And we also threw on a long range radio with a small monopole antenna. So the whole idea was that all of these create like the bare essentials for a tag that can be used to track sea turtles. So something very interesting that I think, did according to what we researched was most of the uh, most of the classic tags have something called a saltwater switch, which is used for detecting whether the tag is above the water or whether the tag is underwater. But we also found out that they use electrodes to like transmit like a small current, and since the seawater is always conducting, that's how it detects whether submersion is occurring or not. So, but the electrodes are also very prone to corrosion because of the salt water, and they also need to be in direct contact with the water. And there are quite a few failures as we have seen. So to solve this, what we did was we used a multi-channel capacitive sensor. So instead of using electrodes as a method to transmit electricity through the water, we just sense the change in capacitance between air and water, which is quite distinctive. So this kind of capacitive sensing, I'm sure many people must have heard about it. It's used to detect water levels in water tanks and stuff. What this also means is that the capacitive sensing occurs through small electrodes that can be waterproof, because the electrodes can sense the change in capacitance between water and air even through something as thick as 3 to 4 millimeters of glass. For the purposes of the turtle tag, a single electrode is sufficient to sense whether the tag is above the surface or below the surface. But in our system, we can use up to 12 electrodes as a redundancy. So in case one electrode stops working, there are 11 more electrodes that can ideally like detect whether the tag is above or below the surface of the water. And the main reason we want to do this is because since the GPS cannot pick up a signal underwater, we keep the GPS turned off by using the capacitive sensor as as a way to know the position of the tag in the water. Also moving on, so I think everybody knows what a LoRa radio is, I'm assuming, but for those of you who do not know, LoRa is the latest generation of radios, which is capable of very long distance radio transmissions with very low powers. It also has very high noise immunity, and it can also transmit a lot of data. More than that, it is also capable of mesh networking. So for us, the idea is that we want to set up base stations across the archipelago, and as and when the turtles move the data, they create a mesh network where the data is automatically transmitted between the base stations and collected at one single point. Another reason is the LoRa radio can operate in open license bands. So for us, it's 865 to 867 megahertz, uh, which means that anybody can operate this without having to get a ham radio license, etc. Moving on. So this is something what we really wanted to share with you guys. So we put a lot of time and effort into designing the tag casing and how the tag is supposed to look and fit on the turtles. So this is the tag that you can see here is the version 1 casing. So this was modeled in-house on Fusion 360 and was 3D printed and further infused with resin. So we also wanted to use something, we wanted to use smooth surfaces and uh, reduce notches and things like that so that the overall drag because of the water is less. Also, we found out that the shape also handles mechanical stress very well. Uh, I also want to quickly dive into how we did the fabrication itself. So we took the 3D model and 3D printed it with a shell of about 10% infill. We purposely did a 10% infill because we wanted to pour the resin inside the shell itself. So the shell is basically a resin with an outer coating of PLA plastic as well. And as you can see, uh, we have multiple layers in which the shell is made. So the shell contains a small battery compartment with its own plastic casing and its own potting. But we also wanted to leave our electronics in a small air pocket because the first versions of our electronics had a depth sensor, which works on barometric pressure as well. And we also have these small channels here at the sides on which the small electrodes would fit, and the small hole is for the antenna. So these tags were about 4 inches in length and about 2 inches in width and about an inch in height. But however, the batteries turned out proved to be very small for our purpose, and the tags were actually dying much quicker than we expected. So for that reason, we decided to upgrade our tags to a larger batteries. So this is our V2 casing, which is a lot less exciting to look at, but it looks a lot more classic. Uh, so we just have a larger battery, a D-cell battery, and as you can see, we have some electrodes that attach to the side. In fact, we have 6 electrodes, and inside we have the electronics with the GPS and the casing itself. So all these also have antenna ports, etc., etc. It's the same mechanism. We've only changed the design so that it can accommodate a larger battery.
Abhi,
However,
sorry to
yeah,
interrupt. We're getting
are we
very
running out
tight
of
on
time?
time. Yeah. So
Okay, last slide. I'm done.
lots of getting you're getting lots of nice feedback, but I'm sorry. Carry
Okay,
on then.
all right. I'm just gonna leave this on for like 2 seconds. Then this is my
Okay,
last slide.
no worries. Oh no,
Okay.
talk us through a conclusion. Yeah.
All right. So far we've done the hardware and firmware integration. GPS functionality has been tested. Submersion sensors have been tested. But however, we've been having troubles with having the tags survive at 20, 30-meter depths in the ocean. So we would love any feedback from the community as well regarding the casing itself. That's the reason I spoke so much about the casing. Uh, so yeah, uh, any feedback would be very welcome. Thank
Okay,
you,
so
guys.
you've got a couple of comments from Robin and Brett. And I mean, Vance just thought it was cool, so I'm into it. So do you want to pick up those comments and discussions in the chat? But thank you very, that was
Sure.
super interesting. Thank you so much.